Good day. Today, let's check a problem from a beam or the problem about the beam. So, a symmetrical beam, as shown in the figure below, it's simply supported. What is symmetrical? Symmetrical means that maybe if you can cut this thing along this x-axis line here, you'll see that this top part will be the mirror image of this bottom part. So, or this top part will be identical to this bottom part. So if that is the case, then it means that this I-beam it's symmetrical about this x-axis. But it's not only symmetrical about that. Even if you can say maybe you cut this thing along this YY line, you'll see that this side will look the same as this side. So if you cut it along the YY, so this thing actually is going to be symmetric about the YY and about the XX line. So it's going to be symmetric about both XX and YY. Right, there is a load. We're going to put something on top of this beam. So the position of that load will be 1 meter from one support. So it can be from these arrows that we see here, they represent the support. That 1 meter can be from here or here, it doesn't matter. So these sub arrows that you see there, they represent maybe the wall. And the wall that the we used to see or we have at homes or at school, the wall of the building, the one that is made from the bricks. Yeah, so we will put a beam on top of those things. So these arrows will represent the reaction force by those walls. A point load of, oh, okay, I've already passed that. Ignore the weight of the beam. So this beam is going to have a weight. Remember, this beam is made from steel. So steel is heavy. So this beam itself will have a certain weight. But in this problem, we're going to ignore that. We're going to assume that this beam doesn't have mass, even so that in reality we know that this beam will have a weight. So now the only load that we will take into account is going to be this external load. This is the external load. So now they say that the allowable stress in the beam mustn't be more than this. So meaning that this load that we apply here, it mustn't cause a stress of more than 65. So what is that stress? That stress is the bending stress. So we know that this thing is going to bend. So if you load this beam we expect it to bend. So it won't remain straight. So this beam will bend like this. Yeah, so as it bends like that, the bottom part, this part here, is going to stretch. So this part here will stretch like this. The top part will be under compression. So this stretch and this compression will only be there when this thing bends. So it will be the result. This tension here and the compression there will be the product of bending. So if this thing doesn't bend, this thing it won't stretch. So that's why we're going to call this stress that will occur there and there. We're going to call that stress bending stress. Now, before we can calculate maybe stress and other variables such as second moment of inertia. Firstly, we have to find the centroid of this beam. So to find the centroid of this beam, we're going to use what we call area moment formula. We're going to use this formula, area total y bar equals to area 1 y1 plus area 2 y2 plus area 3 y3. So this is what we call the area moment. We take the areas multiplied by the distances. So what are these y values? These y values are the distance from the reference to the center of that particular profile in consideration. So y will be the vertical distances. The vertical distances, we're going to use y to represent those distances. But it will be a waste of energy or a waste of time by doing this if we have a symmetrical profile. So like here, if our profile is symmetrical, I mean this profile you can see it's symmetrical. So where these two lines meet here is going to be our centroid, the centroid of this eye thing. So if you want to know the center of this eye thing or halfway, the center will simply be this total height from here to here divided by 2. So if you take this distance divided by 2, it's going to give you this one. So which is going to be the distance from the bottom to the center there. So if you have symmetrical, that's what we're going to do. Just take the height divided by 2 will give you this distance from here to the center. So now let's find this distance. Okay, from here to there I can see is 15. From here to there is 15. Let me find from here to there. How much would be from here to there? So from here to there is going to be half of 230. Remember, total height from here to there is 230. So this distance here will be 230 divided by 2. Okay, let me just use the calculator. 115. 115. So 115 is from here to there. So from here to there will be 115 plus this distance, which is 15. So total distance will be, how much is this? 130. So 130 will be this vertical distance from here up to there. Now, if you, okay, just for learning purposes, let us just do that. Let's calculate the y bar. You will see you are going to get the same answer, so that is going to be a waste of time, as I've said before. But for practicing purposes, let us just do that. So to calculate the y bar, we are going to break this thing into rectangles. So this profile now is like an eye. So what I'm going to do now, I'm going to break this thing into rectangles like this. I'm going to draw a line here like this and like that. So we're going to have about three rectangles, rectangle number 1, number 2, and number 3. So area 1, area 1 will be this area here, which is this rectangle number 1. So area will be this dimension from here to there, multiplied by from here to there. So which is 15. 15 multiplied by 100. 1005. These dimensions, if they are not, they didn't state the unit, they assume or use millimeter. So this will be millimeter squared, but I'm not going to write them. I will only put them at the end, towards the end, or on the final answer. Right, area 2. Area 2, we're going to find the area of this. This is our rectangle number 2. This one here. So we have to find the area of that particular rectangle. Now we do the same thing. The area will be this side from here to there multiplied by from here to there. So that will be our area. So from here to there, as you can see here, it's going to be 10. So you will have 10 multiplied by from here to there, from here to there is 230. So we're going to multiply it by 230. 10 multiplied by 230. Yeah, hopefully it will be 2,000. Area 3. There will be this area here. You do the same thing. It will be this side multiplied by this side. So it's going to be 100 multiplied by 50. It's 1,500. So area total will be area 1 plus area 2 plus area 3, which is 1,005 plus 2,300 plus 1,005. This is 3,000. This 5,300. Good. So maybe now let's find y1, y2, y3, as you can see from this formula. Okay? Y1, y2, y3. So these y values are the vertical distances from the reference. And for vertical distances, always, it's not a must. Your reference can be from anywhere, but always let's make our reference to be this bottom. the bottom of this thing will be our reference. So meaning that these distances will be measured from the bottom. So y1 is going to be the distance from the reference to the center of this box number 1. So we're talking about the center. So at the center of this box number 1 would be somewhere there. So I used to see, I don't know, some authors doing this. Can use draw a line using the ruler like that. Where these cross lines meet, it's going to be the center. So this point will be exactly halfway in the middle of both dimensions. In the middle of this dimension here from here to there, at the middle of this dimension from here to there. So meaning that the vertical distance from the reference to the center here from here to there, from the bottom to this center there, is going to be our y1. Is going to be y1. So y1 will be equal to 15 divided by 2, which is 7.5. That will be y1. So y2 is going to be the distance from the center, from the reference to the center of box number 2 or rectangle number 2. So the centroid of rectangle number 2 is going to be there. So now y2 will be the distance from here to this center here. So from here to there is going to be y2. So how much will be this y2? This y2 will be this distance here from here to there, which is that 15 plus this distance from here to there, we said it's 115. So that 15 plus 115 is 130. That is y2. y3 will be the distance from the reference from the bottom to the center of box number 3. So the center of box number 3 is going to be somewhere there. So when you draw a straight line like this, distance from here to there is going to be y3. So how much will be with this y3? Remember this y3, this distance, this point is going to be halfway in the middle of these two lines. So these two lines are 15 meters apart. So half of 15 is going to be 7.5. So meaning from here to there is 7.5. So now the distance from the bottom to here will be, you will have two options. You can say this distance here, which is 15, plus this distance from here to there, which is 230, plus the distance, plus the distance from here to there, which is 7.5. Or you can simply say the whole length, the total distance from here to there, which is 15 plus 230 plus 15, 260. Okay, 260 is not white ray. You have to subtract 7.5 to get white ray. Yeah, 260 minus 7.5, hopefully it will be 252.5. Let me just add this. 15 plus 280 plus 252.5. So that will be white ray. So that will be white ray. Or you can say the whole length minus this distance here. It will give you white ray. Okay, we can use this one. Now let's substitute into this formula here. Yeah, so our answer now is 130. So which is the same as this one, as I've said before, it's y bar. So here I was just proving that if you have the axis of symmetry, you don't have to do this thing, you will be wasting your time. So you can simply just take the height divided by 2, then you will get the y bar. Now for now, I'm focusing on this xx. I will come back to YY line, this YY line. So for now, I'm only interested in this distance from here, the vertical distance from here to there. So I'll come back to this YY line. Now, okay, but let me just do those things. Let me just find the centroid, the vertical distance, and the horizontal distance. The same thing applies. Let's have said that this side will be the mirror image of this side, meaning that halfway or the centroid of this thing will be from here to there. So the distance from here to there will be the x bar, which is going to be the centroid. So the center of this composite of this I thing will be here, where these two lines meet. So you consider this portion divided by 2, you will have a line here. Then come again, divide this thing by 2 horizontal, you cut it here in the middle. So where these two lines meet will be at the centroid. So the horizontal distances are going to use x. So horizontally from here to there is going to be x bar. From here to the center of everything is x bar. So I'm not going to do that to save time, but if this thing wasn't symmetric, if maybe we were having something like this, if we were having something like this and then you cut it maybe somewhere here, you will see that this thing is not the mirror image of this. So if this thing is not the mirror image of this, you will be forced to calculate x bar from here to there. You will be forced to calculate x bar in this way. Area total x bar equals to area 1 y1 plus area 2 y2 plus area 3 y3. Oh, sorry, it's x distances. So this time, because this thing is symmetric about this y line, we're not going to calculate x bar using this thing. If you want to, you can still use it, but you will waste time. So if you want to calculate y bar, you can do that. I mean x bar, you can do that as we did here. So now x bar will simply be this x bar here will simply be this distance from here to there divided by 2. X bar is halfway, it has to be at the center of this thing. So it's going to be 100 divided by 2. Let me leave the unit, 50 millimeter. So meaning that from here to there is 50 millimeter. So when you measure these distances, x1, x2, x3, x4, make sure that you measure them from one reference. So in other words, the horizontal distances, they will be measured from this right or is left, from this left end. So we're going to make this left end our references for horizontal distances. We're going to make this bottom part, bottom surface to be the reference for vertical distances. So y1 is going to, I mean x1, horizontal distance. X1 is going to be the distance from here to this center here. It's going to be x1. X2 is going to be the distance from the reference to this center of component number 2. So that will be x2. X3 will be the distance from here to this center number 3. So that will be x3. But you can see that the x bar will be equals to x3, will be equals to x2, will be equals to x1. So those distances will be equal. So all of them, they will be equal to 50. Now, let's go to what we call the second moment of inertia. So the second moment of inertia is going to tell us about the strength of this eye profile. So it's a geometric property of a beam's cross-section that measures the strength and its resistance to bending and deflection. So, that here I can't illustrate it, but okay, let me try to draw something here. If you have, let's for an example, take a ruler, the ruler that you use as a student. So it will be like this. So if you apply a force or you put the load here, you will see that the ruler will remain straight. It's not going to bend. You won't see it bending. So let's say you apply the force of, I don't know, let me say 20 Newton. If you take the very same ruler and place it like this, and apply the very same force, you will see that ruler will bend. This ruler is going to bend. So this ruler now is going to, when it's positioned like this, we're going to say that it's going to have less resistance towards bending, meaning that the I value will be small. The second moment of inertia will be small. That's why this ruler will just bend easily under the same load. Maybe don't change the load, just put the same load. But if you put the very same load of 20 Newton while the ruler is placed like this, that ruler is not going to bend, meaning that it's going to have the bigger I resistance. So it means that the ruler, when it's placed like this, is going to have more strength. When it's placed like this, when it's placed like this, it's going to have a lesser strength. So the I value is telling us about that. How easy is to bend that beam? So that is the I value. The I value will be telling us about that. So now we're going to calculate that I value. Then to calculate that I value, we're going to use this theorem. Should I erase this? Because I'm going to need that sketch to, let me see, to explain that this sketch must be fully visible. Right, I have to delete whatever that we discussed before because I have to see this diagram during the presentation. So now let's calculate second moment of inertia. So to calculate second moment of inertia, we're going to use this theorem called parallel axis theorem. Okay, maybe let me do this. Let me break this thing into rectangles. Okay, let me use this space. Yeah, I've broken this I-beam into rectangles, as you can see here. So this rectangle, this portion, it represent this one here. This box number 2, rectangle number 2 represents starting from here up to there. And this top rectangle here will be represented by this. So now we're going to have the center of this, which is this one here, the very same center. The center of this box number 2 is the same as this point. The center of this box number 3, this one is the very same as this one. So we're going to have what we call axis. We're going to draw lines like this, crossing through that center line, center point, through another horizontal line like this. So we're going to call these lines axis. We're going to call these lines axis. These are the axes. Now, we're going to call one of them the XX, meaning that we're going to call this dotted line maybe XX, this one YY, or the other way around. We're going to use this as a guideline. It's not the rule, it's not fixed, it's not a must. But we're going to make XX, or we're going to take XX as the axis perpendicular to the longest dimension. Let me just continue. Good. X will be x axis will be the axis perpendicular to the longest dimension. So let's say x axis or x line. Maybe let's say x line will be the axis perpendicular to the longest dimension. Okay, in this way. In this way. Check here. Remember this box number 1 right, this box number 1 is the same as this one. So this side at the bottom here is going to be from here to there. It's 100. From here to there is 10. So you can see between this dimension and this dimension, or between these sides, the long one is going to be this one. This one is long compared to this one. So perpendicular to the longest dimension, yes, long dimension, perpendicular to it is this red line, is this line. So this perpendicular line, we are going to call it XX. Then this line parallel to long dimension, we're going to call it YY. So this is YY axis, this is XX axis. So you do the same thing here. This is longer dimension from here to there. So perpendicular to it is this line. So this line perpendicular to the longest dimension or to the longer dimension, we call it XX. This one, this red line, vertical one, is parallel to this longer dimension. Therefore, this parallel one, parallel to the longest dimension, we're going to call it YY. So this XX will represent the strong axis, YY will represent the weaker axis. Okay, you do the same thing here, perpendicular to the longest dimension. It's here, we call this thing XX. Parallel to the longest dimension, yes, longer dimension. Parallel to it, we're going to call it YY. You can transfer these things here, provided they won't cause confusion or too much mixture of information there. I don't know. Okay, it's fine. Maybe I can leave it like this. But right. So parallel axis theorem will be written like this. So we have 3 sections or 3 rectangles. So we are going to write it like this. I equals to I plus area H squared plus I plus area H squared plus I plus A H squared. So we're going to have three of these things. Why? Because we've got three sections. Sometimes you'll only have two rectangles. Then we will have to end at 2. We will have to repeat this thing twice. So this time we've got three of them. So we have to repeat it 3 times. Now, I will be looking for the resistance, second moment of inertia of this I thing, of this thing, or of these three boxes combined. So that's why I have XX here. So this XX is this line, it represents this line. So remember, as I've tried to explain with that ruler, every profile is going to have two strengths depending on the how you position that particular supporting member. So I've said that if you place your ruler like this, the ruler won't bend easily, meaning that it's going to have bigger value of I. So when you place it like this and you apply the load here, then you will see that the ruler is going to bend. It's going to bend much easier. Now this one is going to have the lesser value of I if you position it like that. So meaning that every profile is going to have two I values. It's going to have the weaker side and the stronger side. So now we're going to calculate the I value of this profile when this profile is positioned like this. And then we'll come back again and turn it. Put it like this. The same way with this ruler, we'll place it like this and then turn it like this. We're going to do the same thing here with this profile. You position it like this, and then you calculate I. You turn it like this, then you calculate I. But for now, we're going to position it like this, which is this. Then we calculate the resistance of this when it's positioned like that. After that, we're going to turn it to like this. Then after that, we calculate the value of I. We apply the very same load here. Then we calculate the value of I. But that will be with that time we will be calculating I, Y, Y. So this YY line is this one. So at the moment, this we're going to calculate this when this I is positioned like this. This is XX, which is this line. Now, as the name suggests, or as the name implies, I've shown you what are the axes. So we're going to use the axis that will be parallel. Parallel to what? Parallel to this XX. This is the XX of the composite. Every profile or every section or every box, this box is going to have its own XX and YY. This box here is going to have its own XX and YY. So this one, these red ones that we see here, these are the axes of the composite of the eye or of these three boxes combined. Now, to calculate ixx of the composite, we are going to use this individual axis. They are going to help us to find the I of the whole thing. So now, as you can see here, this xx is this line, or is this xx. We're going to take this one as the reference. Remember, when you say something is parallel, it has to be parallel to something. So this parallel thing that we're to parallel axis that we'll be using, they must be parallel to something. Parallel to what? Parallel to this xx. So you will go to profile number 1, which is this one. You will check between this axis, which is this vertical one, and this horizontal one. You will check the one parallel to this xx. I said this xx is our reference. So between these two axes, or between this vertical line and horizontal line, we need the one that will be parallel to this red xx line. So the red xx line goes like this. You come here, you check this xx line, it goes like this. So the xx line is not parallel to this line. It's not parallel, it's perpendicular. We don't use the perpendicular ones. We don't want the perpendicular ones, but we want the parallel one. So when we check this red x-axis like this, then when you come to box number 1, this axis, this y-axis, this one, it goes like this. So that means the y axis here is parallel to this x-axis. So on this box number 1, rectangle number 1, we are going to the parallel axis between xx and the yy. The parallel one is going to be yy. So that's why I'm going to have iyy, because the yy, this yy is parallel to this xx. We go to number 2, you do the same thing. We're here now. So you check between this yy, which is vertical, and this xx, which is horizontal. You check which one is parallel, the one parallel to this xx. So if this line is horizontal, if this xx is horizontal, obviously the parallel one must be horizontal. The vertical one is going to be perpendicular. We don't want perpendicular one, we want horizontal. So that means we're going to use the horizontal axis. This x-axis is parallel to this x-axis. So from number 2, from this, the axis parallel to this xx line is going to be this one. So that's why I'm going to write xx. The same thing on number 3. xx is parallel. Remember, our reference is this xx. This xx that you see here, it represents this xx here. So you go to number 3, you check the axis parallel to this horizontal xx line. This line is horizontal. So the parallel one obviously will have to be this horizontal one here. So the horizontal axis is what? Is yy. So you are going to have y. So this is xx, remember, this is y. So that's why we call this thing parallel axis theorem. We're going to consider the axis parallel to this red xx line. So those parallel axes will be this one, and this one, and this one. In other words, this horizontal line, this horizontal axis. Okay. Now, let me just transfer this for a certain reason. Now, we will see it at the later stage. Let me just transfer. Remember, this box is the very same thing as this one. Let me just transfer this thing. This is the YY line. I'm on box number 2. This horizontal line for box number 2 is this one here, this XX. I'm going to box number 3, this one. Through the center line, horizontal line is YY. Good. So now let's calculate I, which is the second moment of inertia for individual section. This I that you see here, this one, is I for the whole thing, for this I profile, or is I for these 3 boxes combined. So this one is the I for this box. This I that you see here is I for this box. This I that you see here is I for this box. So now let's find those I values for these individual boxes. So as I've said that every profile is going to have 2 I values. It's going to have 2 different strengths depending on how you position it. So the same thing with your ruler, you can test that with your ruler. If you place it the other way around, it will bend easily. If you place it the other way around, it will not bend easily. So that resistance to bending is I. So it will have 2 different values of I. So the same thing with this thing, let's say is that rule. It's going to have 2 values of I. So we're going to have what we call I XX and I YY. So IYY is going to give us the strength of this box or of this ruler when you place your ruler like this. And then you apply force. That will be IXX. Then IYY is going to give us the strength of this ruler when you place that ruler like this. And then you apply force. So this will be YY, perpendicular to the, parallel to the longest dimension. Yes, the longest dimension. So parallel to it is YY. Yes, longer dimension. Parallel to this longer dimension is YY. So this thing that we see here is the cross-sectional area. The same thing with that eye. That eye is this. It represents the cross-sectional area. It represents this side. When you cut this thing perpendicular to the left, you won't have this. So from this, this is that XX line. And then this, and this is that YY line. Okay, the formula for, if we have a rectangular profile, the formula for calculating I will be b cubed over 12. b cubed over 12. Remember, this one will calculate the resistance when the ruler is like this, or when this profile is positioned like this. This one will give us the resistance when the ruler or when this box is positioned like this. Yeah, let me just get the dimensions here. 15 by 100. So from here to this 100. Now, I'm going to use this. B will be the side or the dimension parallel to your reference, parallel to XX. B is going to be the side parallel to XX. So this is your XX line, this one. So between 100 and 15, which one is parallel to XX? This is XX line. So the dimension that will be parallel to x-axis is going to be this one. It's going to be 15. So the parallel dimension parallel to x will be b. So b will be equals to 15 multiplied by this d is going to be the dimension perpendicular to x. So this red line, this one is your x. Perpendicular to x, we have what? We have this side, which is how much? Which is 100. So the side perpendicular to x will be d. You do the same thing with IYY. The side parallel to YY. YY is your reference. This is YY, this line. This horizontal line is YY. So the side parallel to YY, which is this side, which is 100, is going to be your B. The side perpendicular to YY, will be D. So here's YY, perpendicular to YY is this side, which is 50. So sides perpendicular to your reference will always be raised to the power 3. So for IXX perpendicular to XX, it's 100. This is XX perpendicular to it is 100. 100 is raised to the power 3. This is YY, horizontal line, YY. Perpendicular to YY is this side of 15. 15 will be raised to the power 3. So the side perpendicular to your reference will be raised to the power 3. So now, because I don't want this video to last long, I'm going to do these ones quickly. We are done with box number 1. We go to box number 2. We do the same thing. We find IXX. IXX, you check the side parallel to XX, which is this side. I think it's 10. It's 10. So the side parallel to XX is going to be B. It's 10 multiplied by the side perpendicular to XX, which is this side, perpendicular to XX. We're going to raise that side to to the power 3, meaning that is going to be our D. So we said that side is 230, 230. So from here to there is 230. So 230 is perpendicular to XX. So you will have 230 raised to the power 3 over 12. That will be IXX. IYY for rectangle number 2. The side parallel to YY. Yes, YY. Yes, YY. The side parallel to it will be B. So what is parallel to YY is 230. 230 is B. Multiplied by D. D will be the side perpendicular to YY. This is YY. This is YY. Perpendicular to YY is this side. So that perpendicular side, we're going to raise it to the power 3 over 12. So this is IYY and IXX for profile number 2. Then you go to profile number 3, which is this one. You find IXX quickly. So parallel to XX, it's 15. So this side is 15. This side is 100. So parallel to XX, this is XX. Parallel to it is this side, which is 15. Multiplied by perpendicular to XX. Yes, XX perpendicular to it is 100. We raise it to the power 3 over 12. That will be IXX. You will press the calculator there, or you can leave them like that. I will advise you to always use meters. Standard unit for I will be meters. You can leave it in millimeters, but at the end we have to convert it to meters. Meaning that if you use meters right from the start here, you will use 0.015. You divide this thing by 1000, you use 0.1. The same thing with this one, the previous one. So you can use meters. Okay, maybe let me just continue with this millimeters. IYY for number 3, you check the side parallel to YY is this one. Parallel to YY is 100. Multiplied by perpendicular to YY will be your D. Perpendicular to YY is this side, which is 15. Raise it to the power 3 over 12. So after doing this, you come back to this. You calculate IXX of the composite. These are the IXX and IYY of this rectangle separately. So now we have to find the IXX of the composite, those 3 boxes combined. Now this A is going to be the area of rectangle number 1, which is 15 times 100. Area 2 will be the area of this box number 2, which is 230 multiplied by 10, and so forth. So now what is this H? What is this H? So H is the perpendicular distance between the parallel axes. So is the distance between parallel axes. So what is that? H1 is going to be the distance from this XX line, this XX line is our reference. It's going to be the distance from this XX line to this parallel axis. Remember I said those lines, these ones, these are the axes. This is axis, this is axis. So the distance between this axis, between this red XX, this line, and this YY line, this is axis, this is axis. So the distance between this axis will be h. Don't get surprised when they say h is the perpendicular distance between the axes. Check here. This line that I've just drawn is perpendicular to this axis. This line is perpendicular to this axis. So that's why they say perpendicular distance between this axis will be h. So now, what is h1? h1 is going to be the distance from this reference. Actually, h1 is the distance between this xx line and this yy line. So which is the distance from here to there. YY1 is the YY line of box number 1. So the distance from here to the parallel axis of box number 1 is going to be H1. How to calculate this H1? We're going to see the total distance from here to there minus this piece of distance. This distance we said is y1. So this distance h1 from here to there, h1, would be equals to this 130, which is y bar, minus y1. So 130 minus y1, y1 we said is 7.5. Yes, y1. So y1 is the distance from here to the center. So that's how you'll calculate h1. So 130 minus 7.5. 122.5. That will be h1. That will be the distance from the x-axis of the composite to the parallel axis from box number 1. H2 will be y bar minus y2. Actually, it will always be the case. H7 will be y bar minus y7. H20 will be equals to y bar minus y20. So in this case, y bar is 130. What about y2? Y2 is 130 as well. So y2 is Therefore, in this case, H is going to be 0. Will be 0. Check here. Between this, what color is this? Sky blue. This XX line with this sky blue color. And this XX line, which is represented by this red line, red dotted line. When you check those two lines, they are on the same level, meaning that there is no vertical distance between these two lines. Between this purple, this sky blue dotted line and this red dotted line, between this XX line and this XX line, between those two lines, there is no vertical distance. There is no y. They are on the same level. So that's why h will be 0. There is no height difference between those x's. h3 will be the distance from this xx, this red line, from distance between that xx to this yy. So this yy, remember, is this one. This one. So the vertical distance from this axis, this parallel axis to this parallel axis, is going to be h3. So how much will be h3? Remember, from here, from the top to here is 130. And remember, from here to the center here is half of 15, which is 7.5. Not used to this. So now the distance from here to there will be 130, which is this one, minus this distance here, which is 7.5. So that is an option. That is another way of finding that h3. But normally we use this way. You will say y3 minus y bar. That don't get confused here. Here I've started with y bar. Here I'm starting with y3 minus y bar. Why? Because y3, check y3. Y3 is starting from here to there. Y3 is big. So when you check that y3 minus this distance, it's going to give you what? This distance, which is that h3. Y3 from here to there minus this distance is going to give you h3. So y3 is 252.5 minus y bar, or y2. Y bar equals to y2, which is 122.5. Right, now after this, we go and substitute. We have everything now. We come to this parallel axis theorem and substitute. So you will go to those i's that we calculated here. You go for box number 1. These are 2 i's that we calculated. But as we need IY1, IYY for number 1. So you know why we chose YY. So you come here and check IYY. IYY equals to this. So you are going to replace IYY with this one. 115 cubed over 12. That is IYY plus area for this box. It's 15 multiplied by 100. H squared, it's 7.5. H1 squared. H1 we said is 7.5. No, it's 122.5. Sorry. Plus. Now we come to this box number 2. We'll go and check IXX. You know why we chose XX. So you come to number 2. Here we go. It's this one. For 2, box number 2 is this one and this one. So we check IXX. IXX, we're going to use this 10 multiplied by 230 raised to the power 3. Area for number 2 is 230 multiplied by 10. H2, we set it's 0. We set it 0. Plus, we go to number 3. We come here now. IYY for number 3. Here's number 3. IYY is this one. 100 by 15 cubed. So IYY, we will replace it with over 12 plus area number for number 3 is 100 multiplied by 50. H squared, which is H3, is 122.5 all squared. So now you can press the calculator and see how much you get. Good. So after pressing your calculator, that's what you are going to have. That is your IXX. Now we can quickly, because I can see this video is going to last long, you can quickly go and find IYY. So quickly, so our reference this time is going to be the YY line. Remember, our reference has been this XX line, this one. So this time we're going to work with this line, so which is YY line. So we're going to calculate IYY. So we're going to use the very same formula parallel axis theorem. So right, these are the inertias for this beam when it's positioned like this and applying load, and when it's positioned like this and applying load. So the same thing with the ruler. When it's positioned like this, it's going to be weak. So that's why this 2.5 is less, far less compared to this 55. So this 55 is bigger than this 2.5. So when you position a beam like this, it means that it will be too strong. It will be strong compared to when your beam is placed like that. So that is the meaning of this. So after this, that means that your beam, you are not going to put it, position it like this. You are not going to position it like this. But instead, we have to put the load, or we have to use the strong side. So our beam, as I've drawn it up there, we are going to use it, we are going to position it like this. So we're not going to put it the other way around. So this is the strong side. So now on our calculations going forward, we're going to use IXX. We're going to use IXX. We're not going to use this one. This one is weak. This is the weakest side. So if you use this one, your beam will fade, will break, will bend too much. So this one we're not going to use. So this is the formula for bending stress. You can make bending moment the subject of the formula. We're going to use IXX. You will never use IYY. As I've said, IYY it's weak. So if you use IYY, your structure is going to fail. So we're going to use the strong side of the beam, which is that IXX. So you make bending moment the subject of the formula here. You will have this bending stress equals to Ixx over y. So bending stress, it's given, I think it's 65 to the power 6. Iyy, it's 55 point something. 55.216, if I still recall well, times 10 to the power minus 6 all over y. Yeah. So now, what is y? So y is this one. Y is the distance from the neutral axis. So y is going to be the distance from the neutral axis, meaning this centroid. Y will be the distance from here, which is our neutral axis, to the point of maximum stress, or to a point where you will be looking for stress. So our point of interest will be this point here and this point here. So at this surface, top surface, that's where we're going to have the maximum stress. So the stress distribution diagram of ours is going to be like this. So what is the meaning of this? It means that at this point, on this surface, the stress is big, or is the biggest. That's why we say it's maximum. At this surface, check this line is shorter. It means that the stress somewhere here is going to be less. The stress somewhere here, this line is short from here to there. So it means that the stress somewhere here, the stress is not that much. So as you go inward, the stress decreases up until here. Here, the stress is going to be 0. On this line XX, the stress is going to be 0. So this point, we call it neutral axis. At point where the stress is 0, we call that point a neutral axis. It's the point of 0 stress, neutral axis. So at this point, or the material that will be located here, this material will be neutral, meaning that this material won't be in tension, won't be in compression. So that material will just be neutral. It's not going to experience any stretch or squeezing. Now, at this point as well, there will be the change in direction or in nature. When this beam bends like this, the top part from the neutral axis, from here to there, is going to be under compression. The bottom part, starting from the neutral axis to here, is going to be under tension. So the material that will be located below this neutral axis will be under tension. The material that will be located above this will be under compression. So as you know, if you can even fold your arm. When you fold your arm, the top part will be under compression. You will start to see wrinkles developing there. That means there is squeezing. The bottom part is going to stretch. So there will be tension below. So the same thing applies. From here to there, the line will be short. From here to this, the line will be short, meaning that the stress, tensile stress, somewhere here will be small. Then as you go outward, the tensile stress increases. That's why here you see the line being low. So here we are going to have the maximum tensile stress. Stress here on this edge is going to be biggest. That's why we say it's going to be maximum. The biggest stress will be here and there. So when you calculate stresses, unless otherwise specified, you are going to calculate the maximum stress. So maximum stress, which will either be here or here. So what did I say about y? Y will be the distance from the neutral axis to a point where you will be looking for stress. So this will be y. But remember, this part is this one. This part here is this one. So maximum stress will be here or here. So fortunately enough, this distance this time from here to there or from here to there, these distances are equal. It's 130 both sides. So our y is going to be 130 from the neutral axis to this point, to the point of maximum stress. It's going to be 130. So we're going to replace this y by 130. Oh, sorry, convert it to meters, divide by 1000. And calculate the bending moment. Yeah, so I'm getting this 27608 Newton. It can be 27.608 kN. So that is the bending moment. But remember, the question didn't ask us for bending moment. The question is looking for W, the load that must be applied on that beam. So you will have your beam like this. I have drawn it for you in 3D. So this is that beam, I-beam. You will have the supports here, the support. You will have that load, which we don't know, placed at 1 meter from one support. Total length is 4. So if total length is 4, this one is 1, this one will be 3 meters. From here to there will be 3. So now we have to calculate the bending moment for this. All right, so to calculate the bending moment, normally we take reactions here. You calculate the reaction on this side, which is left side and the right side. Or we have a shortcut formula. You can calculate bending moment like this. M equals to the load that will be applied on this beam multiplied by A over B, A multiplied by B over L. So this L represents the distance from here to there, which is 4 meters. This A represents these distances from the load to one side of the support, from the load to here is 1. So you can say from here to there is A. Then B will be from here to this other side, which is B. So B will be equals to 3. So if you use this, W will be equal to, sorry, you replace W by W, we don't know it at the moment. A, you replace it by 1. B by 3. L by 4. So you will have bending moment equals to can say 3 over 4W. So you will only use this formula only if on the beam you only have one point load. Once we have two loads like this, one load applied there, one load applied there, you can't use this formula. So you can't use this. So this formula, you use it when we have eccentric point load. Meaning that when you have a point load not applied at the midpoint, or in the middle, like this one, this point load is not applied here. So we're going to use this formula. But again, the point load must be single. You must only have one point load acting on this. Once we have two of them, you can't use this formula. So once we have two of them, to save time, but you must draw the shear force diagram. Draw shear force diagram, you will have something like this, you will have something like this. Something like this. Your shear force diagram will be like this. So we have to find this point where the shear force diagram crosses the zero line. So at this point, that's where you're going to have maximum bending moment. So you will take moments here. Okay, now to calculate W, you remember this is the bending moment. This one is the bending moment. Then this one is the bending moment. So to calculate W, you will say M, this M equals to this M. So 27.608, okay, times 10 to the power 3 equals to 3 over 4W. Then from there you solve W. W would be equal to this, make W the subject of the formula, it will be this multiplied by 4 divided by 3. So the point load that must be applied there will be 3, 6, 8, 10. 3, 6, 10.6. 0.6 Newton. So in order not to exceed that stress of 65 MPa, our load must be equal to this or less than this. Remember, this is the stress limit. The stress must not be more than 65. So for stress to be 65, the load must be this. So to be safe, in order the stress not to exceed this much, you must make sure that the load that you place there, that you apply there, that load mustn't be more than this value. It can be anything less than this. So this will be the maximum load to be applied on that beam. So I want to show you alternative of calculating the bending moment. But that is the traditional way. That is how you used to calculate the bending moment from science 4 and so forth. I'm worried about this video is taking long. I will try to be quick. But what you can do here is that one of calculating the maximum bending moment the same way you used to do from the science 4. as I wrote here, the maximum bending moment will be high, or the bending moment will be high or will be maximum at the point load. So once we have something like that, if you want to find the maximum bending moment, we have to take moment at that load. But only if you have a single load on that beam. If you have a one load on that beam, then the maximum bending moment will be at that point. So at that point, that's why we have to take bending moment. So that is when you have something like this, eccentric load. So this one, when we have simply supported beam, having a load at the center, exactly at the center, halfway, to calculate the bending moment, the maximum bending moment, you have to take moments at the center. Or you can use this formula, WL over 4. For this one, where the load is not acting at the center, the maximum bending moment will be WAB over L. Or if you have this thing, you have to draw the shear force diagram. You draw the shear force diagram. Your shear force diagram generally will be like this. We will have the force there. We don't know reaction at the left. Then you draw this. You come here. You will have downward force. It will be like this. So at this point, which is this point, or at this point where the shear force diagram crosses this horizontal line, that's why we are going to have the maximum bending moment. So to calculate the maximum bending moment, we have to take moments here. So to take moments here, which is what we have to do when we have to calculate directions there, you will say, you take moments here, you will say this force L, we don't know it. You will say L multiplied by, okay, you will be calculating the maximum bending moment. Maximum bending moment will be equal to this reaction here on the left hand side multiplied by the distance from here to there, which is 1. So the maximum bending moment here will be this reaction L multiplied by 1. Or you can consider this side. When you take moments here considering this side, you will have this reaction R multiplied by 3. Right, remember this is just an alternative solution. So after this, you can equate this one or this one. Both of them, they will give you maximum bending moment, which is this. You can equate this thing to 27608. 27608. From this, you take this divided by 3, you will get the reaction on this side. Or this one will be equals to the reaction on this side, 27608. That will be the reaction on this left hand side. So after this, you can come and say clockwise moment equals to anti-clockwise moment. Clockwise moment equals to anti-clockwise. So you can take a moment here at R. Let's take moments at R. So when you take moment at R, clockwise moment will be that force 27608, which is this force here. It's a clockwise moment multiplied by the distance 4. From here to there will be 4. Equals to anti-clockwise. Anti-clockwise moment will be this force, which is that W. W multiplied by the distance from R to there will be 3. So that's how we'll find W. W will be equals to 27608 multiplied by 4 all over 3. So we made this thing before. So W will be equals to that, which will give you this 368 10.6. So that was the alternative way. If you don't want to use this formula or this route, you can use this route. Right. That is the final answer. The question was looking for that, was looking for W. Yeah, so that marked the end of this lesson. Thank you.